Today we're going to talk about a theorem in calculus called the intermediate value theorem that finds its basis in continuity. Once you've established continuity, then you can apply the intermediate value theorem to prove things about solutions. But remember, it has to be a continuous function first. This is the formal definition of the intermediate value theorem. A function that's continuous on a closed interval starting at a and ending at b will take on every value between f of a and f of b. In other words, if y is between f of b and f of a, then some c would have to match up for that in the x interval. So let me see if I can try and explain that a little bit better. So let's suppose that you have an a point on a continuous function, and it's the smaller value. And let's suppose that you have a b point also on the function, and it's the larger value. There's lots of values between a and b, but we're going to pick one and we're going to call it a c value. So it's somewhere between a and b in the middle. Okay, remember, a is the smaller, b is the larger, c represents anything that would be in between. If the function is continuous, then you can guarantee the following. That f of a, which is the y value that goes with a, and f of b, which is the y value that would go with b, that the y value that would go with c would be somewhere in between those values. And moreover, you're guaranteed every y value you could possibly find between those two values would be traced back to a c value that was originally in the interval. So it actually is really helpful to work ourselves backwards. Let's see if we can draw it visually. All right, so if we start at a, which is the smaller of the values, and we trace it up to f of a, all right, that's the point. And we also have b, which is the larger of the values, and we trace that up to f of b. Assuming, and it has to be continuous, if the function is continuous between those 2 points, then you can find a y value that's also between f of a and f of b and trace it back to a c value that would be between those two. Okay, it's really not so much about starting at a c value and going to find the y value. It's more of finding the y value and being able to go back and find the c value. Okay, so if you can find a y value between those two, you should be able to trace it back to a c value. That, in a nutshell, is the intermediate value theorem. But it only works if there aren't any breaks. It has to be connected, unbroken, no jumps, okay? No separate branches, okay? No asymptotes. It's got to be continuous, otherwise this intermediate value theorem doesn't work. And it's so important that it's continuous, that's like the equivalent of stating the indeterminate form at the beginning of a limit. That is worth a point in and of itself. Just stating the indeterminate form and doing the work, that's part of the rubric. And so if you're going to use the intermediate value theorem, you have to state explicitly f of x is continuous. Then you can continue. If you leave that part off, then you lose the point for that and you can't get full credit. It really invalidates everything that comes before it. All right, so let's look at some practical examples. So notice how explicitly the problem states that this is a continuous function for g. The question, given the table for g, we know here are some sample values. It's not all the values, but it's the sample values. The question is, would there exist an r within the interval 0 to 2 for which the g value of r would be 5? In other words, we're supposed to start with a g value, which is the y value of the function, being equal to 5. Could I then prove backwards that that must exist? I don't have to find it, I just have to prove that it is there, that it does exist somewhere. So here's how we're going to go about that. You clearly state, since g of x is continuous, I will use the intermediate value theorem. So you start with the number 5. And can you put that between any values from the chart? It's like, oh, well, there's a 7 and there's a 3. So 5 is between 7 and 3. 3 is the f of 2. 7 is the f of 0. So since 5 is between f of 2 and the f of 0, and since this 5 is the y value, then I should be able to find an r value in between 0 and 2 as x values. Now you might be noticing I just switched the order of that. If you look at the table, this is a decreasing table. The values of this table, the y values go down, but the x values go up, right? 0 to 2, 2 to 4, those values go up. 7 to 3, 3 to negative 6, those values go down. And so when you're referring to the y values, f of 2 is smaller than f of 0. But when you refer to the x values, 0 and 2, you gotta switch them back out, and so that they're in the correct numerical order. So yes, I can work my way backwards. And the answer to the question is yes. The reason the answer to the question is yes is because you were able to show two y values that had the right y value in between, connecting those back to the x values that it goes with. Oh, let's try another one. It gets easier the more often you see it. Let k be a function defined as a piecewise function this time. Okay, so this is the pieces. Must there exist an x between 0 and 2 for which k of x could be equal to 4? Well, first we have to establish continuity. Is k continuous? Well, let's look at the pieces of k. Since the pieces of k are both linear, all right, x plus 2, x plus 4, those are two lines. Those two lines are connected. Okay, those two lines are continuous, okay, are by themselves, but are they connected? So since they're both, linear, k might be continuous. So then check the limits, the one-sided limits. So we're going to check the limit as x approaches 1 from the left of k of x. And we're going to check the limit as x approaches 1 from the right of k of x. 1 from the left would be plugging 1 minus plus 2. 1 from the right would be 1 plus 4. 1 minus plus 2 is 3 minus. 1 plus 4 is 5 plus. No. K of x is not continuous because the left and right hand limits don't match each other. so the IVT can't be used. And we can't use the IVT to prove that there must exist an x between 0 and 2 for which k of x equals 4. Okay, this is not a continuous function. All right, let's try another one. Let f be a function defined by the parabola x squared minus 4x plus 1. Find an interval a to b in which f of x must be 0. Well, first of all, we have to establish if f of x is continuous. So, since f of x is a parabola, it's continuous. That's the definition of a parabola. Now our question is, can we find an interval in which f of x must be equal to 0? So we're going to work our way backwards. If f of x is going to be equal to 0, then it has to be less than a positive number and greater than a negative number. It must be, and these are y values, right? A positive y value, because f of x is a y value, and a negative y value. I need to find a and any positive y value on the function, and I need to find any negative y value on the function. And this becomes some trial and error. F and f of x. Let's just try some. Let's plug 0 in. If I plug 0 into the equation, 0 squared minus 0, I get 1. If I plug 1 into the equation, I have 1 squared minus 4, which is negative 3, plus 1, I get negative 2. I've got my positive, I've got my negative number in the y value terms. So if f of x is between less than or equal to 1 and negative 2, okay, 0 is between those two things, right? Hopefully we all agree that 0 is between those two. And 1 is the y value at 0, and negative 2 is the y value at 1. Then there must be an x between, and we're going to switch the order again, 0 and 1. Can you picture that? This is a parabola, and I want to know, where does it cross the x-axis? Where does it have an x-intercept? That's what it's asking for. When f of x equals 0, that's an x-intercept. This function, if this is the x-axis here, there's 0, it's going from 0, 1 to 1, negative 2. This parabola is connecting those 2 points, which means that it has its x-intercept somewhere between 0 and 1 is where it crossed the x-axis. Let me just help you frame this a little bit. You know, picture Isaac Newton here. He didn't have a calculator. You guys have a calculator. You can do second trace, calculate 0, and you can find exactly where a graph is crossing the x-axis. Newton didn't have that. He could find an interval where it crossed the x-axis. It's got to cross between 0 and 1. I know that because I know that the value at 0 is positive, the value at 1 is negative, and since it's continuous, it had to cross over the x-axis somewhere. It's not possible to get from point A to point B without crossing the x-axis. You call this point A, you call that point B. It's not possible to get from point A to point B if the function is continuous without crossing the x-axis. So Newton could narrow it down. He could find the interval between where there was an x-intercept. Okay, then he refined his method and he could, narrow it down further. But that's why on your calculator to this day, when you are doing calculate a zero, you're asked for a left bound and you're asked for a right bound. Your calculator needs to have a narrow window to look at in order to find what that actual x-intercept is. And it's using Newton's exact method of coming up with what that intercept value actually is to a very accurate level. Okay, lots and lots of decimal places. So the idea of the intermediate value theorem, first of all, you must clearly state that it's continuous. Second of all, you need to find two y values that are on opposite sides of what you're looking for. If you're looking for 0, then you find a y value that's positive compared to a y value that's negative. If, like in the first example, you were looking for 5, you look for two y values that are on opposite sides of that value. Once you find y values on opposite sides of your target, what you're looking for, then you'll be able to work backwards and have your x interval that guarantees the existence of that value. All right, good luck with that. You've got the long weekend coming up, and then we can talk more about this on Wednesday, when we Zoom together next. All right, hope you guys have a good holiday weekend, and I will see you next week.